So I want to talk a little bit here about these absolute extremes for a two-variable function, and has been our modus operandi. We've been making correlation to between a two-variable function and a one-variable function. In a one-variable y equals f of x scenario, just to do one example here, let's say I've got a function that starts at 0 and then maybe we'll just go out here and let's just call it, let's go out there to 10. So if I was going to ask what is the absolute min and max here, well, what we'd see is that the absolute max occurs out here at f of 10, right? Because it's just the largest function value there is. And then the absolute min, again, for this particular domain, going from 0 to 10, well, it occurs here, and let's just call that what it was, okay, 8. F of 8. So one of the absolute extremes occurs at an endpoint, and then the other one occurs at the critical value, critical number. Well, that's the one variable y equals f of x scenario. Same thing can happen on a two variable function. So the absolute extreme can occur for the two variable. So those can occur at, guess what? At an endpoint, at a let's call it a critical point. Right, because when we're talking in a two variable equation, we need an x and a y, and so absolute extreme can occur at a critical point or at an endpoint, which, as you'll see in our scenario here that we do, the equation that we do, it's more like a boundary point. And you'll see more what we mean by that in just a second. So, but it's the very same idea. So, yeah, the critical points give you those local maxes and mins, relative maxes and mins. But when you go to the absolute case, it could occur. It could occur at a critical value, or it could occur at an endpoint, just like it's easier to visualize it in the two-dimensional space. This is 3 dimensions we're in, but same idea. A lot of times the 3 dimensions builds on the 2-dimensional, so same sort of thing. All right, so let's just do one, and it gets a little tricky, you might say, but not too bad. All right, so find the absolute extreme, absolute max and min. For f x y equals 2x plus 2y minus x squared minus y squared. On set D, where D is the closed triangular region. One thing, problem itself is wordy. Closed triangular region with vertices 0, 0, 0, 9, and 9, zero. Okay. So like we said, the critical points are easy, so relatively speaking, but the boundary points, that's where it gets a little trickier. So we're going to do our, well, let's first of all, let's draw region D here. So D is just the domain, if you will, or the set over which we're finding these extrema. So it's 0, 0, 0, 9, and 9, 0. That's the vertices, so we're talking about this triangular region, like that. And so that's what we're saying. We need to look at the critical points, but we also need to look at the boundary points, which means any point on the boundary of this triangle. So there's three lines that make up this boundary. So I need to check things on the boundaries, points on the boundaries, and then the critical points, and endpoints. So those are the three. So we're going to check the function values at the critical points, the endpoints of or vertices, I guess a better way to put it, because those corners, and then boundary points. And we'll explain how we do that along the way here. But critical points, we've covered those, so let's get those. Start with the easy ones first, I guess. All right, so how do we get the critical points? Well, let's do it down here because I'll need my board, I think. Well, the critical points, you set the partial derivatives equal to 0. Partial with respect to x would be 2 minus 2x. And then the partial with respect to y, I think it's the same except for y, 2 minus 2y. Is that right? Everybody okay with those partials? And then we want those equal to 0, which in this case are fairly easy solving here. So that's just going to mean x is 1, right? Solve that for x and solve that for y, and y is 1. So our critical point here is 1, 1. And so we're going to have to check the function value of 1, 1. That's one of them. Now again, like I said, the vertices, those are automatic. If you've got those are automatic. You check those. Which are 0, 0, 0, 9, and 9, 0. So far we've got four of them to check. There's a couple others, and those are the boundary points. And this sort of thing kind of comes up in the future too, so it doesn't hurt to kind of look at it. All right, so let's just start with line 1. So let's think about points on boundary points. I better give myself a little bit, finish this out. All right, so for line 1, that boundary, the points are in what form? Well, it's a vertical line, and so points on that vertical line are always going to be of the form, what, x is, so if you just take one particular point, that would be 0, comma 1, 0, comma 2, all the way up to, so it's 0, comma y would be the form of that, which means then our function values are f of 0 y's. See what I did there? So line 1, the points are always of the form 0, comma y. And so I'm just going to plug 0, comma y into the function, which makes it 0 plus 2y minus 0 minus y squared. So my function, in a sense, kind of shrinks down. Now, that then, if we think about critical numbers from that, you know, just do, since it's just one variable now, you can just think about the derivative. F prime of 0y would be 2 minus 2y, and then set that equal to 0. So again, that's going to be y equals 1. But this y equals 1 goes with x is 0, so that would be another point to check, 0, 1. Because it's on the boundary, and it's kind of the critical point of that boundary. So there's, how many we got so far? 5. So we're just finding those. So that's a boundary point we need to check. What's another one? Let's go to line 2, which I did the horizontal one there. So line 2 would be what? X comma zeros? 1, 0, 2, 0, 3, 0. So that's an x comma 0. And so f of x comma 0, well, that shrinks it down to 2x minus x squared. So if I do the derivative of that, that's 2 minus 2x, which that's going to give us x equals 1, which means we'd have 1 comma 0. Makes sense. So there's a 6th point to check. And last but not least, we got line 3. Well, line 3, save the best for last because, all right, it's a slanted line, sloped line. I need to come up with an equation for that. How about a y equals mx plus b for that? Well, I know the b is, the y-intercept's 9. What's the slope? Well, if you do rise to run, you fall -9, or fall 9, run 9, down 9, then the slope -9 over 9, -1. So that equation for that line is y equals -x plus 9. Well, what would points be on that? Well, if I call the x value x, then the y is -x plus 9. Like I said, it's the most complicated of the 3 there. Yeah, so if I just pick an x, then the y value is -x plus 9, which makes the function a little more complicated. So f of x comma -x plus 9, well, I got to plug in y to be -x plus 9. So that's 2x plus 2 times -x plus 9 minus x squared minus -x plus 9 squared. Maybe just about as easy to get the derivative off of that instead of trying to simplify it, but let's see what would that derivative be? 2 -2. Oh, that might work out pretty good. Yeah, those are going to cancel. Might have been easier. All right. Let's just go with what I did here. Minus, stay. All right. Minus 2x, and then then bring down the 2 minus x plus 9 to the 1 times -1. Second, this comes out. Those cancel. Like I wanted to here. The x's just cancel out. Because that'd be plus 2x, and then, because you got a minus. Oh no, it's minus. That's right. Because you got 3 minuses there. Yeah, this is minus plus 18. That's my derivative. Minus 4x. So I set that equal to 0. And that gives me negative 4x equals negative 18. X is negative 18 over negative 4, 9/2. Which, if you plug that in, negative 9/2 plus 9 gives you 9/2. That makes sense there or not. But, so the x value we get for the critical number, if you will, is 9/2, and if you plug that in, the y value turns out to be 9/2. So then, yeah, 18/2. Yeah, so there's a 7. We're up to 7 here. Just 7. 7 points to check. That's all. Yeah. So the extrema are going to occur at one of those because we've got critical points and the boundary points. So we need to check check the function value at each one of those. Let me see, let me get them written down here. I have to erase something. This is as good as anything. All right. So, yeah, we're just going to compute f of 1, 1. And then compute f of 0, 0. And then compute f of 0, 9. 9, 0. 0, 1. 1, 0. And 9/2, 9/2. See which one is max. Which one's min? So it's a little bit involved, but it's not that complicated, I guess. So f of 1, 1, 2 plus 2 minus 1 minus 1. Is that 2? 0, 0. That's easy, that's 0. 0, 9, so that would be 18 minus 81. Negative 63. 9, 0, I think we get the same thing. 18 minus 81, negative 63. 0, 1, so that would be 2 minus 1, that's 1. 1, 0, I think same thing. And then, funnest of all, 9/2, 9/2. Well, 2 times 9/2 is 9. 2 times 9/2 is 9. Minus 9/2 squared, so 81/4. Minus 81/4. Whatever that gives me. Got 22.5 one time or another. I think it's a while ago. Yep, negative 22.5. So, what's our absolute max? Right there, f of 1, 1. Absolute min, f of 0, 9, which is also the same as f of 9, 0, negative 63. There you go. Lots to check, but, and you can see here yeah, the absolute max occurred at the critical point, right? 1-1 was a critical point. 0990, that was one of the vertices, so two of the vertices.